All right. Good afternoon, everyone. I'm Shan Liu from Beijing Institute of Open Source Chip. I'm a hardware design engineer with 7 years experience in semiconductor industry. Today, it's a pleasure to introduce you to RISC. That is our solution designed to power the next generation RISC-V AI solutions. Here is what we will cover for today. First, I'll walk you through the background about the AI market. Second, I'll introduce you to RISC, specifically about its objectives. Next, I'll talk about the technical details about our open source hardware stack. Finally, our RISC-V AI IP solution. Background. Let's start with a quick overview of the current AI landscape. On the right, you can see the data from NVIDIA GTC 2025. The answer is obvious. NVIDIA continues to dominate the AI market. Since 2021, the number of developers and AI downloads has doubled. And the AI startups are up by 171%, and GPU-based applications have grown by 118%. Besides GPUs, there are other emerging AI hardware platforms. However, the ecosystem is fragmented. We have diverse instruction sets and hardware architectures, NPU, GPU, TPU, DPU, etc. And the software stacks vary by architecture, which increase the learning curve of our users. Thirdly, the operator coverage is limited, making the migration costly and difficult. Finally, the collaboration between the AI chip vendors is lacking. This is where RISC comes in. Born to tackle these very challenges, RISC stands for RISC-V AI Computability Ecosystem. RISC is launched in 2024. Its mission is to standardize the AI-related RISC-V instructions, break hardware-software fragmentation, accelerate RISC-V AI adoption. There are 4 objectives of RISC. Firstly, the ISA standardization. Secondly, the software stack development to build an open source framework of software. Thirdly, the AI IP core design. We are targeting to support RISC-V V+T+M SoC architectures. Finally, the ecosystem collaboration. We try to connect upstream and downstream of the partners for RISC-V AI product commercialization. Okay, here's to show you the current status of RISC. We have brought together over 40 companies and institutes to contribute across different domains, including Matrix Group, Tensor Group, SIMT Group, Software Stack Group. All right. In the following 2 sections, I'll talk more about the technical details from software side and hardware side. We'll start with the software stack. We are building our software stack through Triton approach. To those who don't familiar with Triton, Triton is a Python-based language and a compiler for writing high-performance GPU code. It is widely used in deep learning, especially for custom kernels like flash attention and efficient transformers. This is how does our stack work. At the top, we support standard AI frameworks, for example, PyTorch and TensorFlow, and then it is compiled to a hardware agnostic IR, meaning that the AI logic is decoupled from specific hardware. This IR is then lowered into backend IRs for GPUs, TPUs, NPUs, etc. Finally, we use LLVM to optimize this representation for different instruction set architectures before execution. You can tell this approach offers high portability and reusability. For the same ISA extension, we can reuse the entire software stack. Even for different ISA extensions, like Matrix or Tensor extensions, the front end remains the same. You can see it here, and we just swap up the back end. This keeps our software modular, maintainable, and scalable as the ecosystem evolves. Okay, last section, we'll shift gears and take a look at our RISC-V AI solution. Some background knowledge. We are targeting AI inference. So let's look into the large language model inference first. This picture shows you the LLM inference pipelines. It's a little bit complicated, but the conclusion is very simple here. You can see the LLM inference pipelines have the major inference stage of refill and decode. And operations like GEM and softmax dominates these stages. And finally, it maps to RISC-V AME, RVV element device, and RVV reduce. The conclusion here is that RISC-V AME and RISC-V vector enables RISC-V-based LLM inference. Another background is the technical trends of today's LLM. It also deserves our attention. Here listed some key points. The first point is the attention mechanism are evolving. We are seeing innovations like group query attention, GQA, and multi-head latent attention, MLA. Comparing to traditional multi-head attention, these techniques can cut memory bandwidth by 50 to 80%. Another major development is flash attention 3. It optimizes performance by overlapping GEM operation with softmax, minimize latency in the attention pipeline. What's more, we are seeing increased adoption of low precision formats like FP8, int8, and even int4. This is not only reduced memory usage, but also enables 2 to 3 times higher performance for GEM. In the end, the MOE, the mixture of experts models, are becoming a go-to for scaling models. They can match the performance of dense models while activating only a fraction of the parameters, that is 2 to 4 times fewer to be specific. And the key deployment of MOE is the expert parallelism, EP. It helps distributes expert computation across devices. This strategy has 2 benefits. It makes large-scale inference cost-efficient. Secondly, it calls for distributed inference capability like RDMA and infinite band. With this background, we have our RISC-V AI solution. Again, our goal is to target AI inference, and with 2 scenarios, that is the distributed inference in cloud, low latency inference for end user. This is the block diagram. We have a Scala core used for control and general purpose operations, a matrix core, and a long vector unit. The matrix core and long vector units are loosely coupled. They operate independently from the Scala core pipeline. All these cores share a high bandwidth L2 cache here. The L2 cache acts as the communication bridge between the compute units. You can tell the design balances parallelism, flexibility, and scalability. Let's go through a real example to help you better understand our solution. So at the beginning, the Scala core dispatches instructions to the matrix and vector cores. The vector core performs GEM using data from L2. The vector core executes softmax, also access L2. For examples like flash attention 3, like I mentioned before, the vector core and the matrix core works in parallel. The matrix core handles QT, transpose, and PV, while the vector core does the softmax. This parallel execution model reduces latency and increases throughput, especially for transformer-based models. This is the detailed block diagram of our vector core. It's a little bit complicated, but I'll walk you through together. So the blue box here are very standard pipelines: decoder, issue queue, dispatch, and vector load store unit to access L2 cache. These are the yellow block is the register file. The green block is the execution unit. So the vector core receives instruction from CPU. It goes through these 3 stages to generate a macro-ops. The macro-ops will be dispatched into the load store unit to access L2. Then the load store data will be stored in the register file. It depends on cases. It may need to be rearranged. The data needs to be rearranged. After that, the data will be sent to the execution unit. Also depends on the cases. You may need to do cross-LAN execution. The left-hand side shows you some parameters of our vector core. We have 32 banks with 64-bit per bank. The VLAN is 2048-bit. For the compute units, it has 32 LANs with 64-bit per LAN. So the DLAN is 2040-bit. Here also shows you some throughput number for FP32. The throughput is 64 elements per cycle. For FP16 and BF16, the throughput is 128 elements per cycle. For memory bandwidth, it is 2048 bits per cycle. Matrix core. The matrix core receives the AME instruction from the Scala core and does the decoder, issue queue, dispatch, as well as similar as vector core. These 4 yellow blocks are for execution. The MMAU does the matrix multiply accumulate operation with the int 8, floating 8 MMU. What worth your attention here is that the FP8 accumulates to FP32 with full mantissa for better performance. EWU is the element-wise unit, which will be implemented in the future. This is for miscellaneous task, and this is for the matrix load store unit for L2 cache. Okay, the last part is the high bandwidth L2. We are targeting 128 to 512 byte per cycle. Some spec of our L2 is configurable from 1 MB to 4 MB. The protocol is directory-based tail-link cache coherence protocol. 16 MSHR per slice. The performance is 64 byte per cycle per slice with 8 slices. It's going to be 512 byte per cycle. Here also shows you some memory bandwidth number from other Scala cores, just to give you a sense what does the high bandwidth mean here. Okay, last slide is about the SoC reference design. Our design is targeting 8 to 16 cores so far, connecting via CHI protocol to enable coherent NOC integration. Our memory model follows RVWMO, and we aim for full open MP support so that the existing multi-threaded software can be easily ported. This is just an example design with 8 cores of our SoC system.
So we have to come to an end.
Yeah, this is the last one, sorry. FYI, our AI solution is under development. We will have more technical details during China Summit in July. And visit us at booth 41 to learn more about RISC. That's all I have. Thank you for your attention.